Hello everyone, and welcome to the second part of Shannon's paper. If you didn't hear or watch the first part, so it's down in the description of this episode. Enjoy! I'm trying to understand what I'm reading, and I don't even can think about like meta, how it's related to other stuff. So it's cool that you have those insights. Okay, so I continue with the paper. It says, that's important. We can think of a discrete source as generating the message, symbol by symbol. It will choose successive symbols according to certain probabilities, depending in general on preceding choices, as well as the particular symbols in question. A physical system or a mathematical model of a system, which produces such a sequence of symbols governed by a set of probabilities, is known as a stochastic process. Okay, so now he introduces stochastic processes. This is your PhD, Mike, no? So,
Yeah.
So number 3 reference is your PhD. Well, let's see what's number 3. He gave reference here. Let's go back. It says, see example, stochastic problems in physics and astronomy. From someone named Chandar Sehar in 1943. Cool. So the process that makes the let's say the sequence is called a stochastic process. We may consider a discrete source, therefore, to be represented by a stochastic process. Conversely, any stochastic process which produces a discrete sequence of symbols chosen from a finite set may be considered a discrete source. So this will include such cases as, and he gives the example of languages, various let's see,
number one is NLP.
Yeah, natural written languages.
Natural written languages.
Yes.
And NWL.
Yeah. That's another word for it. And NLP is a marketing term, right? He wasn't doing marketing here.
Yeah. Then he gives an example of quantized television signal, or PCM transmitter, which PCM is something you remember here? Yeah, some kind of exactly. I forgot. I also knew in the past as an electrical engineer. Okay, number 3. Mathematical cases where we merely define abstractly a stochastic process which generates a sequence of symbols. So he just gives examples like of A, B, C, D, E, and he gives probabilities to each one, and then he shows us various examples of possible sequences. Then he changes the probabilities in another example, and now we have a different sequence of letters A, B, C, D, E. So that's less important. Then he gives example.
I think that classical NLPs are based on these concepts of probabilities per word, probabilities per letter, and so on. And the fact that he's giving such simple examples, it means to me that it was never been written before. So he has to introduce this as in the most basic terms to the readers.
Interesting. I guess most of the NLP guys today are not aware of this paper, and they're not aware that Shannon did some NLP kind of 80 years ago.
No, he's the father of NLP.
Yeah. That's actually true, because NLP is natural language
processing, right?
Processing, which what he does here. Today we're doing next word prediction, etc., right? Or next letter, next token, whatever.
Yeah. But what are we talking about here? We're talking about probabilities pair. He's saying letter or parts of letter. He just doesn't call it token.
Yeah.
Right?
Yeah, because token is just a subword, Yes. What we are doing today, we are not explicitly modeling these probabilities. We are just trying to represent our language in some embedding space, because trying that trying to model all these probabilities isn't feasible. You can't just build a huge table with all these conditional probabilities. So if we can build some lookup tables, so we choose to model it by some machine learning models, and this is the modern NLP.
Yeah. But if you go, Mike, if you go to, let's say, I don't know if it's classical, prior to deep neural networks in NLP, you had like n-gram and various algorithms in NLP that, in a sense, resemble this idea, because he talks here that some of them could have like a memory, right? So like the next word or the next letter depends on the previous one and the frequency of the previous, and then you can go even two back. So the frequency of the previous one.
He has a chapter called Markov processes.
Yeah, exactly. We'll get there.
It is an order Markov process, right? Because your conditional probability depends on the n last symbol, right? It's not a classic Markov chain.
Right. I think that's what we do these days, but I think he presented it as just one. But he said there can be a situation when we depend on the past also.
Yeah.
Not just the there is n-gram structure, number 5.
Here.
Yeah. And we call in NLP, I think we call it n-gram algorithm, like in classical terms.
Yeah, exactly. It's the classical prior to deep.
Prior to all the deep, yeah. So he's the father of NLP. That's nice to know.
It is a great stuff. I think I saw it several months ago. I think somebody just posted it on Twitter. Only this page, only all these texts in English, and then I saw this second order approximation. It looks like it is very similar to some English text. You know, it is not. It is illogical text, and there is no. It is not semantically correct, but still it looks like English. You know, it is just second order approximation.
Yep.
Yeah, I want to show something interesting here that he says. The first two samples, so he gave like samples of random letters that follow the rule. He says were constructed by use of a book of random numbers, right? Because again, we can do it easily. We have whatever, Python or etc. We can give those examples. So he uses a book of random numbers to generate the letters. Then he says to construct number 3, which is interesting, which is second order approximation. So like the next word depends on the previous, or the probability of like the previous word. So in order to do that, which again without computer is difficult, he says one opens a book at a random and selects a letter at random on that page. This letter is recorded, he writes it down. The book is then opened at another page, and one reads until this letter is encountered. The succeeding letter is then recorded. Turning to another page, the second letter is searched for, and the succeeding letter recorded again. So again, he does this second order concept that each letter depends on like on the previous one. And then to get it randomly, he like, uses a book. That was cool. When I read it, I'm like,
it is really cool.
What you had to do without computers.
Yeah.
Without actually use your brain.
That's true. That's true. Yeah.
Okay, cool. So we get to chapter number 4, a graphical representation of Markov process. Sorry. Yeah, today it's with a V, but here in the paper it's Markov. So he's Russian, Mike. What do you say?
According to his surname, he was Russian. I think it was a quite famous Russian mathematician who lived in the beginning of the 20th century. I guess I don't know much details about him, But
is it Markov or Markov?
This is, in Russian, it sounds like Markov, not Markov. But but I'm talking about how does it sound now? I don't know how did it sound 100 years ago. Maybe 100 years ago it sounded like Markov. Today it is hard to say Markov. I almost is Markov. So, but I can hardly know how it was 100 years ago. You know, it was a long time ago.
Cool. So we won't go into the definition. But again, it's a stochastic process that the present state depends on the previous state, right? That's like the most general representation or explanation. Do you agree?
Yeah.
Yep.
So he gives examples here because, again, maybe back then to the communication community, no, they didn't know about Markov processes, so maybe he had to give a longer introduction. So actually does it here. Let's see what's important. It says here, all the examples of artificial language given above are ergodic. The properties relate to the structure of the corresponding graph. It shows a graph. So ergodic processes, I have like a 2-sentence explanation. I'll tell it to you and tell me if it makes sense. So just a funny story, when I did my random signals course, we had a question about ergodicity in the exam, and I didn't succeed. So maybe my explanation is not good, but I think I came with it later. So a process is ergodic if you can take, let's take example, a coin. I can take one coin, let's say it's a fair one, I can flip it 100 times, one after the other, write down the results, calculate the statistics, and get, I don't know, the probability of heads. The process is ergodic if this is what I gave you, the 100 flipping of coins is equivalent to taking the same coin 100 times and flip it at once, get all the results, and calculate the statistics. So if I can do that, it means the process is ergodic. And he says here, it's similar to the channel that makes the symbols or the signals in a probabilistic way. You cannot make 1,000 physical instruments and make it all the signals in one. So you make it one after the other. And when he says it's ergodic, as far as I understand, he means that it's similar to it making them all at once out of what 1,000 or 1 million sources. So what do you think about my understanding?
Yeah, that's the hand waving type definition of ergodicity. That the time.
That's why I'm here.
Yeah. Yeah, no. We're not going to dive in deeply into it because it's involved, but it's exactly what you said, that the time, the mean or the average across time is the actual expectation of the population, which is not trivial.
Yeah.
It's not something that we usually can assume. And that's exactly what you said. That's ergodicity in the mean, I think it's called.
Actually, as a former mathematician, I have some hurdles in understanding this hand wavy definition. For me, as far as I remember, ergodic process is a process which converge to some steady state distribution. It is the first condition. So if you are running this Markov process for enough time, you can tell what is the limiting distribution of each value this process can have.
Okay.
And the second one, and very important, he's talking about it, is it's very, very long word in English, irreducibility. And the reducibility means that you don't have your Markov chain, which is splitting into two separate Markov chains. You know, for the odd. For example, you can think about Markov chains when Markov chain that then you are throwing some coin and you get one, and on the odd let me explain it.
On the odd flips.
Yeah, on the odd flips you can get some specific numbers, and on the even flips you can get some other numbers. So it converges to some measure, but this measure is not regular, so it must be irreducible. So you should be capable of getting to any state of your Markov chain. This you know, last time I read about the ergodic process, it was 15 years ago. So this is what I remember. To some limiting distribution and the irreducibility.
Yeah, I think first, perfect for saying that, and I would just say that it wasn't so important in the following derivation, so I didn't see it a lot or at all later, but I stumbled here and I said, okay, that's there's a cool story behind it. So let's continue. It gives examples, and now we move to chapter number 5, which titled Choice, Uncertainty, and Entropy.
Yeah.
It's almost like the American dream, liberty, freedom, and what's the third one?
Pursuit of happiness.
Yeah, exactly. So instead of that, we have better. We have choice, uncertainty, and then entropy. Let's go. So he says, we have represented a discrete information source as a Markov process, the one that makes the signal or the sequences. And he says, or asks, can we define a quantity which will measure in some sense how much information is produced by such a process? Or better, at what rate information is produced? Okay, so he gives us motivation for what will come later. He says, suppose we have a set of possible events whose probabilities of occurrence are P1, P2, up to Pn. We have n occurrences. These probabilities are known, but that is all we know concerning which event will occur. So again, we just know the probability of each event. Can we find a measure of how much choice is involved in the selection of the event, or how uncertain are we of the outcome? Again, more motivation. If there is such a measure, say capital H, as a function of all the probabilities, P1 up to Pn, it is reasonable to require of it the following properties. So he's saying, let's assume we have it, this kind of measure of information produced by the source or uncertainty. It should have the following properties. This capital H should be continuous in the Pi, in the probabilities. If all the probabilities are equal, so each probability Pi equals 1 divided by n, so it's a uniform distribution, then H should be a monotonic increasing function of n. With equally likely events, there is more choice or uncertainty, then there are more possible events. Okay, did you understand this, let's say, property? Assuming I'm flipping a coin, right? So Pi, I have two options, head and tails, each one is half. So what does it mean H should be a monotonic increasing function of n? N in the case is number of messages.
I think I'm not thinking about the coin. I'm thinking about
coin is a bad example. Forget it.
Yeah, I'm thinking about Pi as for example, if n is equal to 10, so we have 10 events, and each one has a probability of 1/10, and you have 100 events, and the probability of each event is 1 divided by 100. I think that uncertainty that you have in the second case is much higher, because you have 100 different possibilities, so it is quite natural for me. And one is natural as well, because we like continuous function. And actually, I'm struggling to find some intuition for 3. Maybe.
Okay, let's read it.
Yeah.
If a choice be broken down into 2 successive choices, the original age should be the weighted sum of the individual values of age. Okay, and there's like a plot, like a tree of possibilities, and it shows some kind of a property, which again, not sure that I understand also this property.
I think it is not about understanding, it is about finding some intuition. I understand the formula, I understand the graphs, but I'm struggling to find some intuition, because I have a feeling that it's very, very intuitive. Nir, do you have some ideas?
I look at it as a probability tree, and kind of like decision tree, if you will. Okay, and each and every branching out is a conditional probability. And it's like, I see it as the law of total probability here, which we can do the same thing with entropies, because we are operating on a logarithm scale, and we can add them all up, right?
Okay, it actually makes sense. I need to think it over, but it really makes sense. I didn't think about it, but it really can remind the total law of probability. It is.
Okay, so I'll read it again. It says, if a choice be broken down into 2 successive choices, the original age should be weighted sum of the individual values. So because we have successive choices, then we should multiply probabilities. But because we are working on age, which you define as the log of the probability, then we will add them.
Yeah.
Cool.
Interesting.
Okay, then he says in appendix number 2, the following result is established, and it's called theorem number 2. The only age satisfying the 3 above assumptions is of the form, and he says, it's written, age equals minus capital K times sigma, so it sums over n of pi, the probability of each event, times log of pi. Okay, so it's like we said log of pi, it's the information, as far as I remember. I think that was somehow the information. So it takes the information, times it by probability of this, I don't know, pi is an event happening, and then sums all over them.
Actually, it is just an expectation of.
It is expectation.
Pi, if
pi, it's pi. It's pi.
Yeah, the log of pi. It is
Yeah.
a conditional expectation. If you are putting it this way, it is an average of the amount of bits you can represent, the average number of bits.
That's
you need
right.
to represent these probabilities which define this probability distribution. So it's
because information is in bits. Yeah, so it takes every event times the bits in that event that represented, which is the log of the pi. Yeah, that's an interesting way of looking at it. Let's see if he gives us some.
By the way, this definition of entropy is It's something that we use a lot in machine learning, right?
Yeah. I think there are almost no paper in machine learning which did not use this entropy in some way or another.
Exactly, yeah.
He says the form of H, the entropy, will be recognized as that of entropy, is defined in certain formulation of statistical mechanics. And he cites number 8. Let's see who's number 8. Tolman, Principle of Statistical Mechanics. Okay, from 1938. It says where Pi is the probability of a system being in cell I of its phase space. Okay, now he talks about statistical mechanics.
Yeah.
H is then, for example, the Boltzmann famous H theorem, but it says we should call entropy. He cites again, he writes the equation, the entropy of the set of probabilities, Pi to Pn. If x is a chance variable, we'll write age of x for its entropy. Thus, x is not an argument of a function, but a label for a number. To differentiate it from h of y, say the entropy of the chance variable y. I'm not sure what he means by chance variable here.
A chance variable is a random variable.
So he says like, okay.
That's how they call it the 100 years ago, probably 75 years ago or whatever. They call it
75. Chance. Okay, so entropy of a random variable x is defined as we said log
h
of I. Yeah.
What he said is that h of x is not an argument for the function h. Actually, the arguments are the p sub I.
Exactly, it's the probability distribution of that.
Yeah, it just he's clearing the notations here. That's it.
Okay. Then we get a specific case when we have two possibilities, P and Q that equals 1 minus P. So not fair coin, at least a general coin. And then he plots, again, back then probably it wasn't easy. The x-axis is P, the probability of getting, let's say, heads, and it varies between 0 and 1. And on the y-axis is the entropy in bits. And then he shows that when we have half, so an equal coin, we get the maximum amount of entropy. Why is that? Give me the motivation.
Maximum uncertainty. Yeah.
Because you
go ahead,
don't
Mike.
know maximum uncertainty in what?
When you flip a coin and it's a fair coin, you can never predict that your prediction is it's like what we discussed on a classifier, right? When the ROC, the ROC curve of the classifier, let's say is binary classifier, okay?
Yeah.
We're talking bits here. So when it's a straight line and y equals x or PD equals PFA, detection equals false alarm, then the classifier is just noise. It's just flipping a coin, right? We have maximum uncertainty, and and so if we transmit a system that flips between 1 and 0, we need 1 bit for 1 and 1 bit for 0. That's what it means. If we transmit in a system that the probability of 1 is actually 1 and the probability of 0 is actually 0, we don't need any representation, because we know it's deterministic. That's why the big number of bits are 0. That's the entropy. And conversely, when the probability of 1 is 0 and the probability of 0 is 1. And in between, so for example, if you go to 0.1 in P, in the x-axis, you see that it's about 0.5 bits. That's the entropy. So why is that? It's because you have 0.9 chance that you transmit 1. If you have 0.9 chance that you transmit 1, you don't have to transmit 1, 1, 1. You can do something more smart, like Mike said before, is, for example, transmit number 1 once, and then the number of times it repeats itself, because it will repeat itself 9 times out of 10, right? So
yeah,
you can,
it's like run length encoding or something like that.
Exactly. So what he
whatever
said
it's
is
called.
that you can code it if you know them. If you know how to do it smartly, you can reach the 0.5 bits.
Yes.
It doesn't say that we know how to do it, but that's the optimum, let's say.
Exactly.
Entropy is basically measuring uncertainty. Entropy is going up, uncertainty is going up.
Yeah, uncertainty of the source that generated those messages, right? Or those signals.
Yes, but I think of it as uncertainty in probabilities of a random variable.
Random. Okay, cool.
No,
Got it.
if you take a look at the formula for entropy for this coin, for the case that P is equal to 0.999, P multiplied by the previous formula, not this one, the formula beforehand in the previous
This?
stage, this one. And
Yes.
and you take a look on these two summands and P, and imagine that P is equal to 0.999. So P multiplied by log P is almost 0. What does it mean? It means that you need almost 0 bits to represent 0. Why? Because with a very high certainty, you know that your signal will be composed of zeros. And sometimes one of the 1,000 zeros will have some one, but you don't need 1 bit per zero. You need practically 0 bits for 0. And then here you have some, and then you compute q multiplied by log q, and q is equal 0.001. Then you need to allocate some bits for 1, but for 0 itself, you need to allocate almost 0 bits, and this is the essence of this encoding. This is the essence of the entropy.
So in a sense,
we use this all the time, Daniel. We use this even right now on the call. So our images, for example, my image here, almost everything is constant except me moving my hands. We're not transmitting each and every pixel all the time. We're transmitting only what moves in the image, only what has more probability of flipping the state.
Yeah.
Okay. Exactly. So that's exactly what he's talking about here.
Yeah. So just see that I understand. Again, I understood your motivation and what you explained. So if log P is what we said, let's say in information, and it's unit of bits, now entropy is some kind of a weighted sum of bits. So that's why the measure for entropy is also in bits. Right? So yeah, just to get the relationship between them. Okay, let's continue.
Actually, I think about entropy as a measure of information as well. Okay.
It's a weighted information, no? Because we see here.
Entropy, if you will.
Yeah, like
exactly.
it's
yes.
This is information, and this is weighted. Like that's what Mike said as the expectation value of the information.
You know, I'm sure what I'm going to say is 100% correct, but uncertainty and information are causally correlated and some kind of proportional. The more uncertainty you have, the more information you can create. You can't create too much information if you have zeros. If you have 0 with probability 0.999, but if you have some fair coin, your information contents are much higher. This is at least how I understand it.
Yeah, I'm not sure, because also when people say natural language information, when they say uncertainty, when they say entropy, and then actually formalize them as something else. So I get what you're saying. I know there is connection, right? And like it feels right, but I'm not sure what does it mean from a mathematical perspective.
Maybe our listeners would fix us.
By the way, there is the concept of information gain in decision trees, right?
Yes.
When you learn the algorithm decision trees, you
have
also
entropy
learn-
there. No,
yeah, of course. It's nice, huh?
So
yes.
Yeah, it will be cool once we go over the paper in the future of decision trees. Let's see if they cite Shannon.
I'm not sure, but we'll check it.
Then he talks about number 3. It is, why it's number 3? Suppose the two events, X and Y, with M possibilities for the first and N for the second. He talks about, okay, he says let P of ij be the probability of the joint occurrence of the I for the first and J for the second. Then it defines the entropy of a joint event. So it's entropy of X and Y. Okay, and then he says, assuming we have like a joint, so we can think about it as a joint probability distribution of a random XY variables, and then we can do conditional ones. So we can marginalize by Y and get the entropy of X, or marginalize by X and get the entropy of Y. So it just, again, similar to probability theory. It says it is easily shown that, usually it means it's like 5 pages.
Oh, no, it is really easy.
Okay, cool.
This one is really easy.
I think it's easy, yeah.
It says that the entropy of the joint distribution XY is equal or less than the entropy of X plus the entropy of Y.
Okay, I have a small remark here about the information.
Yeah.
As I said, we are not sure whether I was correct or not. But if you look at this formula, if you are looking as H, X, Y as a sum of information which is hidden in X, Y, and it is less than the sum of the informations which carries X and which is carried in Y. It is very natural because you have 2 bags of information, and then you aggregate it. You can't create more information. You can't aggregate more information on the sum of the information in 2 bags. You can create less if you have some mutual information which is mutual, which present in the both bags, but you can't create more. And there is, by the way, very interesting notation. Very interesting the notation of mutual information. I'm not sure it is discussed in this paper, but it is a really interesting notation. So so maybe I wasn't so incorrect about it, about the connection of entropy and the information.
No, who said you're incorrect? Yeah, I think you were correct.
I'm not sure I was correct. I need to check it.
No. I think that entropy is information.
Okay.
Entropy is information, and what you see here, by the way, what does it resemble? This thing is there is an equal sign only if they're independent, right?
Exactly.
Yes. So this is like saying P of xy equals P of x times P of y when x and y are independent, right? Yes. When they're not independent, what do we have there? We have the conditional probability. So here we have the conditional entropy as an addition here to be equal. It's kind of like we teach in probability theory with the intersecting the Venn diagrams. Right?
But in probability we multiply,
but
here it's logarithm, so we add.
Yes.
Yep. Exactly.
It is
I like it.
Logarithmized, yes.
Yeah, and it's exactly what you said. The information of both cannot be greater than the information of the sum of them.
Yes, interesting.
Yeah.
Okay. I think we need to stop here because it is 10 o'clock.
Yeah, exactly. What was my next sentence?
Okay.
We need to go and watch some
Final of
champion
Euro Championship.
finals. Yeah. But cool. I think we did half, so I'll be able to break it down into 2 or maybe 3. We'll see. And then next week we're gonna continue, guys.
Yes, from this page.
Yeah. So let's see.
Yep.
Yeah, we have a little bit left, and then we'll move to the next chapter. Okay,
Yes.
cool.
Nice.
Perfect. Was fun. It's better to do it as a team to go over this paper.
Undoubtedly.
Oh, by the way, here is the conditional. So that's exactly what I said before.
Yes.
He's writing it. I didn't remember it in the paper, but yeah.
Exactly.
Okay, we'll go over it again next.
Okay.